So let's work on our second problem today. And this is a problem that you might have been familiar with if you've ever tried to charge your air conditioning system with a bottle of refrigerant. You're going to have some sort of refrigerant line, and there's going to be some sort of port here, maybe a valve, and you're going to connect a bottle of refrigerant, which we're going to replace with this little rectangle here. So this is going to be liquid. Now we're going to use R134A here, and we're going to say it's a 5 kilogram container, and it's at 24 degrees Celsius. Okay, and what we want to do here is this line is going to, this refrigerator is going to go out into this line to charge it up, to fill it up. Okay, so let's read the problem statement. It said an air conditioning system is to be filled from a rigid container, rigid little container of R134A. If you want to stop, just search for R134A. You'll see them in Walmart, little cans, but this is going to be a rigid, a bigger container, a 5 kilogram container of liquid R134A. The valve connecting this container to the air conditioning system is opened until the mass of the container is 2.25 kilograms. So we're going to start here with state 1, that we have mass 1 is equal to 5 kilograms, and our temperature 1 is equal to 24 degrees Celsius. And we're going to go to a state 2, and let me put it over here. State 2, that we're going to have that the mass 2 is equal to 0.25 kilograms. And when the mass hits 0.25 kilograms, we're going to close it. We're going to close that valve and not let any more of the refrigerant go out to the system. Okay. During this time, only liquid R134A flows out of the container. Okay. Only liquid flows out of the container. So the state that's exiting is going to be liquid R134A. Is all flowing out. And it says, presuming this process is isothermal while the valve is open. Okay, so we're going to say that the temperature exiting is going to be 24 degrees Celsius, and that state 2 is going to be temperature at state 2 is going to be equal to 24 degrees Celsius. Okay, so we have an isothermal process. We're saying that refrigerant does not change temperature. 24 degrees Celsius, state 1. Put it on the container, open up the valve, 24 degrees Celsius R134A comes out into the line until we have a container that doesn't have as much R134A in it, but it's at 24 degrees Celsius. That is an isothermal process. What they want us to figure out is the total heat transfer for this container. And I gave this on the test a few semesters ago, and students would say easy, 0. If it's isothermal, there's no heat transfer. But that is not correct. Isothermal is temperature, not heat. Okay, so what's going to happen here, if you've ever done this, if you've ever taken a bottle of air, have you ever bought a bottle of air to clean out something, and you turn it on, and as you let the bottle of air go, and you press the valve on the top of it, let the air out of it in that compressed container, that container gets cold. Why does it get cold? Because heat from your hand is going into the container. Okay, so in this situation, the R134A, if you were holding it, they're trying to get that to go into the AC line. Heat from the surroundings is going to go into the container to keep the temperature at 24 degrees Celsius, because if not, the temperature is going to drop. So we're trying to find out what the required heat transfer is here. So we have to think through the process. Okay, so we start with our equation. The change in mass of the control volume with respect to time is equal to the summation of my mass flow rates in minus the summation of my mass flow rates exiting. Okay, and we're going to integrate this from 0 to t dt, from 0 to t dt, and from 0 to t dt, because it's a transient problem. The mass is changing. I should say we're looking at this container is my system, so the mass is changing. It's the energy in this changing. We can't use a steady state process. Okay, so we can make this simple. We can say if there's no mass coming in, and this dt is going to go away. And so this is going to give us mass of the control volume at state t minus mass of the control volume at time 0 is going to be equal to mass exiting. And so mass 2 minus mass 1 is equal to mass exiting, and we know how much that is right now. 5 minus 0.25, 4.75 kilograms of R134A is exiting. Don't need really an equation to figure that out, but that's what this equation will tell us. Okay, second equation, the change in internal energy of our control volume with respect to time is equal to Q dot minus W dot plus the summation of the mass flow rates in, enthalpy in, minus the summation of the mass flow rates exiting, enthalpy exiting. I'm already getting rid of all kinetic or potential energy effects. That's what we've kind of standard protocol that we've gone as we've gone through these. We've gotten rid of these things. Okay. We know that there's no work because it's a rigid container. And we're going to integrate this from 0 to t dt, 0 to t dt, 0 to t dt, 0 to t dt. And so if we do this, dt's cancel, we're going to get the internal energy of our control volume at time t minus the internal energy of our control volume at time 0 is equal to the heat transfer, not the rate, because we're assuming it's constant, goes out of the integral. The rate times the time which the rate is applied, it gives me an amount. Plus, what did I do in here? I should get rid of this term. There's no mass coming in. So there's going to be minus the mass exiting times the enthalpy exiting. Okay, so I like to write this as U2 minus U1 is equal to Q minus mass exiting enthalpy exiting, or mass 2 U2 minus mass 1 U1 is equal to Q minus mass exiting enthalpy exiting. Now we're putting in terms of specific internal energy. And remember, because the mass is different in state 1 and state 2, we have to write this equation. So we have these two equations that we have gotten ourselves down to, and now we want to take these two things and we want to put them together. And if we put them together, we're going to get that mass 2 U2 minus mass 1 U1 is equal to Q plus, let's see here. Oh, I made a mistake, didn't I? And I made a mistake. This should be a negative. This should be a negative mass exiting. Okay, because this negative has to come down here. It has to come down here. So I'm going to replace mass minus mass exiting with M2 minus M1, which is going to give me a plus. M2 minus M1 times enthalpy exiting. See if you catch me on there. This is where, again, I wish I had you there to yell at me during class. Hey, you forgot the negative. Okay, so this is going to be my equation I'm going to govern with. I'm going to work with this. Okay, let's highlight what we know. I know the mass of state 2, and I know the mass of state 1. And I know the mass of state 2, and I know the mass of state 1. Can I set the state in internal energy 2, internal energy 1, and enthalpy exiting? Okay. Well, I know state 1, it's all a liquid, because it says here liquid. It is a liquid. So I know that for state 1, I could do liquid approximation. Absolutely. And I know what's leaving. I said only liquid leaves the situation. So this one's liquid here, so I can do liquid approximation. So these two are pretty easy to deal with. State 2, I'm not sure. I'm not sure what's going on there. So let's go back to here and see what's happening here. So state 1, this is going to be the internal energy of the saturated liquid at 24 degrees Celsius. And the enthalpy exiting is going to be the enthalpy of the saturated liquid at 24 degrees Celsius. And these two values, this is going to give me 82.37 kilojoules per kilogram. Remember, we're dealing with R134A. And this HF is going to be equal to 82.90 kilojoules per kilogram. So that gives me that now I know this one and now I know this one. I need to find out what my internal energy 2 is. Now, how do I find that? Well, I know my mass at 2 is equal to 0.25 kilograms. And I know my volume at 2, it's a rigid tank, is equal to, I don't know my volume. I don't know my volume. But I know my volume is equal to my volume of 1. So if I can find my volume, because I know that volume of 1 is going to be equal to mass 1 times specific volume of 1. Okay, so that's going to equal 5 kilograms times the volume of 1, which is going to be equal to the specific volume of the saturated liquid at 24 degrees Celsius. Okay. So this is going to be equal to 5 kilograms times, if I look at this value, it's going to be 0.8257 times 10 to the minus third meters cubed per kilogram. Again, I want you to look this up. I'm saving time and probably I think most people can get this, but if you need that assistance, if you can't figure out this, then we need to talk and make sure we can get that before Monday night once again. And so now I can find this is going to give me a volume of 0.004128 meters cubed. Very, very small, but that, I mean, it's not, I mean, we're talking about meters cubed, it's huge. I mean, huge container, so that makes some sense. And so I can go back here and say, well, if I know V2 is equal to V1, if I take V2 divided by my mass 2, I can find out what my specific volume is at 2. Okay, and so I'm going to do that. If I take this volume and I take this mass, so I'm going to have 0.004128 divided by 0.25, I'm going to get a specific volume of 2 that's 0.016514 meters cubed per kilogram. And I know this is my specific volume at state 2. I know that my temperature at state 2 was 24 degrees Celsius. This is my temperature at state 2. So now I know 2 things, and I can set the state. And what I'm going to find out when I set the state is at 24 degrees Celsius, this value for specific volume is between a saturated liquid and a saturated vapor. It is a liquid-vapor mixture. Okay? And so this is going to give me that I'm at a liquid vapor. And then I have to find the quality. And the quality that they'll give me here is going to be 0.508. So by mass, half of that can is going to be liquid and half that can is going to be vapor. Okay, when I'm at the very, very end of my time there. All right, so that's a very important thing. If we turn this can upside down, the vapor portion is at the top, the liquid portion comes down to the bottom. But now I know the quality. And since I know the quality, I can find all other states. So using that quality X, I can then find out what U2 is by using the UF plus X times UG minus UF equation. And that gives me that my internal energy of 2 is going to be 162.47 kilojoules per kilogram. Okay. And that's my missing unknown. So I want you to follow this last 3 minutes of process because this is important. Rigid tank volumes are the same. Mass changes. So I can calculate my new specific volume. I know that specific volume and the temperature that I'm at. I can find out where I am in the system. And that seems I'm a liquid vapor mixture. Whenever I'm a liquid vapor mixture, when I'm on that line, I need to figure out the quality. I calculate the quality. Once I know the quality, I can find everything else. I can find my internal energy. Okay, and that's my missing unknown that I can have. Come on now. I want to, oops, computer. down to the end here. And we're slowing way down. This is the problem that I really have to solve. I thought I had it solved. Sorry about this, folks. So this is now my U2 value. Okay, my U2 value. What I want you to do, come on, slowly, gently move up here. What I want you to do, come on, don't be like that. If you are at home and you know what's going on here, it's something about my computer. When I'm connected via uh, internet crossover cable to my desktop. It's going there all the time. I think it's just working too hard. I just need, but it never did this. I mean, it's weird thing. It's never done this over the summer. Never has done this last semester. This is just a new phenomenon over the last few weeks. Whatever the case may be, we now know everything in that previous equation that I had right above here. I now know U1, U2. I now know mass 1 and mass 2. I know the enthalpy exiting. I know everything except for Q, and I want you to calculate Q. And remember, the sign for Q should be positive because there's heat transfer coming from the surroundings into the system to keep it at a value. So please provide that value for me. That'll be what the quiz question for this problem will be, find the heat. And then we're done with today's lecture. Okay. I will work and make sure this computer issue gets fixed. Okay. Until Monday, have a happy weekend. Be safe, be healthy, have a good time grading, good time studying, and we'll see you at least Monday night at 7